All right, so today what we're looking at is major evidence of major crustal change. And what I'm defining that as things that you'd have to make observations over a large area to notice them. All right. Now, one of these things, some changes, things like faulting, individually that would be a local event, or a fold, or a particular volcano, that'd be kind of a local event. But if I take all the data from a whole bunch of earthquakes and a whole bunch of volcanoes and stuff like that, and I plot those on a map, what I find is that they don't just happen randomly, right? What I find is that most of these changes happen in certain areas, right? So most earthquakes and volcanoes and mountain ranges where you have some changes taking place happen in these certain zones, and where I wouldn't know that unless they had data from a whole bunch of different locations. But it's usually on the coast of the continents and the oceans. Usually that's where it happens. So you can see on the west coast of North America, west coast of South America, over here in Asia. There are some exceptions, but by and large, most of the activity, most of the changes are happening in these certain areas. And we call these areas as zones of crustal activity. All right? All right. Now, earlier when we looked at minor crustal changes, one of the features we looked at was something called a syncline. And a syncline was basically when rock layers pushed together and they folded downward like that. All right. Now, for the most part, synclines are relatively small features. They might be, they might be like a few hundred feet or even just a few miles. All right. Now, there's another feature that looks kind of like a syncline. It kind of has a down dip in it like that. But this is typically a much, much larger feature, more in the hundreds of miles kind of size. And this feature here is a result of downwarping, right? Now, even though it has basically the same shape as a syncline, what's causing that is completely different. So synclines are caused by the rock layers being pushed together like that. What downwarping is caused by is when you have layers that are sinking as a result of overlying sediment. All right. So basically, a place where, let's say you have a river, and the river's carrying lots and lots of sediment, and the river goes into the ocean. All right. That sediment doesn't get spread evenly throughout the ocean. The place where most of the sediment's going to get deposited is, shortly after it enters the ocean. So you're going to have lots and lots and lots of sediment getting deposited there. Well, sediment is heavy. So you end up with a spot where you have a whole bunch of material being deposited that's really heavy, where areas maybe a few hundred miles to the east or west of there might not have that much material getting deposited. So what happens is all that overlying sediment becomes heavy, and that weight pushes down on the rock layers, bending it like this. All right. So that feature is a result of downwarping, the weight of the overlying material pushing down on it and causing it to dip like that. And again, this is a much larger feature than a regular syncline. So I'd have to have data from a large area to notice this. Now, with this downwarping, usually if it's in the ocean, that sediment gets deposited there, and this sediment was most likely going to stay there and eventually at some point turn into rock. But another place where you can get downwarping is not caused by sediment. It can be caused by ice, right? Glaciers. Glaciers can be a couple miles thick. And if I have a spot where a glacier's sitting on the bedrock, that can cause the rock layers to bend down like this. Now, the difference between a glacier and sediment is that the sediment, for the most part, is just going to stay there. Glaciers, as time goes by, they melt. And once they melt and the ice is gone, the rock layers have bended down, But now there's nothing there that's going to keep them down. So what happens as time goes by is the rocks slowly kind of rebound and go back into shape like that. And that's what's actually happening in the area around New York. Is we were covered by glaciers around the Great Lakes area. We were covered by glaciers, and the glaciers cause the rock layers to bend down like this, but the glaciers are gone now, so we're getting glacial rebound where the land is slowly uplifting to go back to its original shape because there's nothing heavy on top of it anymore. Right? So downwarping is a major crustal change. Next, ocean floor spreading. Ocean floor spread from regions of mid-ocean ridges. All right. Now, in the ocean, or in the oceans, there are a bunch of mid-ocean ridges. So on this map here, here's the mid-ocean ridge right there. There's the mid-ocean ridge right there. And there's one down the middle of the Atlantic Ocean right there. All right. So there's a bunch of ridges in the oceans around the world. Since we live closest to the one in the Atlantic Ocean, I'm going to probably refer to this one the most. It's called the Mid-Atlantic Ridge. But the same things happen with other ridges too. All right, so at these ridges, the ocean floor is spreading apart. Now, how do we know that's happening? What evidence is telling us that the ocean floor is spreading apart? Well, one is if you look at the age of the igneous rock on the ocean floor. Now, the three types of rock, igneous, metamorphic, and sedimentary, the only one you can easily find the age of is the igneous rocks. You could do some radioactive dating on that and get a good age of that. But anyways, so if you take, let's say here's the Atlantic Ocean, here's the Mid-Atlantic Ridge, and like over here would be like North America, like over here would be Europe. If I take rock samples starting in North America from the bottom of the ocean floor and I find the age of them, the ones by the continents are going to be fairly old. And as I get closer and closer to the ridge, the rocks get younger and younger and younger and younger until I find the youngest rock right at the ridge. And as I pass by the ridge and start going to the other side of the Atlantic Ocean, I'm going to find the rocks get older and older and older and older again. Right? So the youngest rocks are near the ridge and the older rocks are near the edges. Now, how that tells me that the ocean floor is spreading apart is the age suggests that what's happening is new rocks coming up and pushing the old rock off to the side. New rocks coming up and pushing the old rock off to the side. More new rocks coming up and pushing the old rock off to the side. And the fact that like if I go like 100 miles this way and find the age of the rock, and go 100 miles this way and find the age of the rock 100 miles this way and the rock 100 miles this way are going to be the same age. That suggests that this is happening. Right? So the fact that you have the youngest rock at the ridge and the oldest rock towards the continents, that suggests that the ocean floor is spreading apart. Another thing that suggests the ocean floor is spreading apart or at the ridges is the reversal of magnetic poles. Magnetic minerals line up with the poles. All right, so we'll come back to this in a minute. For right now, we're just going to look at magnets. All right, so first off, some rocks are like this guy here, and what I mean by that is if you look closely, there are a bunch of staples that are sticking to this rock. Now the reason why these staples are sticking to this rock here is because this mineral rather, the reason why they're sticking to this mineral is that this mineral is magnetic, right? So some minerals are magnetic. Now, here I have a compass. Okay? Now, compass, it's magnetic. The compass needle is slightly magnetic. The Earth produces a magnetic field, and what that compass does, the compass needle lines up with the magnetic field of the Earth. And so this side of the needle right there is going to point towards the magnetic north. This side points to the magnetic south. So if I turn it like this, it's still pointing to the same way. No matter how much I rotate the compass, it's still pointing to the same way. Right? It's lining up with the Earth's magnetic poles, so that way's north and this way's south. Right? Now, if I get another magnet near it, like for example this magnetic mineral, then I could throw it all out of whack, right? Because right now the magnetism from this mineral is stronger than the Earth's magnetic field just because it's close to it. But if I take it away, then it'll line back up the way it's supposed to. Right? So anyway, so you can see the Earth has a magnetic field. Now, how that works? Okay. Well, the Earth is a lot like a bar magnet. All right. Now, a bar magnet has a north end and a south end. Now, the significance of the north end and the south end is if I take another bar magnet and I try to put two north ends together, the two magnets repel each other. Right? Doesn't want to get near this one. Okay. If I put a north end near a south end, then what's going to happen is they come together. Okay. So what's happening at the north end and what's happening at the south end of a magnet's different. Now, I could show you the magnetic field of a bar magnet with this guy right here. Okay. So here's a bunch of those metal rods, and if I put a bar magnet on there, all right, I put a bar magnet on there, what you should see is you can actually see the magnetic field around the bar magnet. So if you look at all these things, they're all kind of lining up like that. They're all kind of lining up like that. They're all kind of lining up like that, like that, like that. That's the magnetic field around this bar magnet. Well, the Earth has a magnetic field around it just like that, all right? And that's why, compasses will point to the north and so forth. They're basically doing what these little things right here are doing. They're lining up with the magnetic field, all right? Now, I'm going to put another one of these things up here, but it's going to be a little different from this one in that this one here is this one here has a bunch of little compasses in it. Okay? So I put that on there like that, and it's basically like the other thing. You can kind of see the magnetic field, all right? But now these guys, if you look, these are little compasses. They have little arrows on them, all right? Now, some of the little compasses are broken, so it's not perfect, but you kind of generally see the pattern there. Now, look at a few of these little arrows from the compasses, and what I'm going to do is I'm going to take the magnet, I'm going to flip it around. And what you can see is that now the little arrows point in the opposite direction. If you focus on one of them, when I flip the magnet, the little arrows point in the opposite direction, with the exception of a few of these which are broken. For the most part, the arrows point in the opposite direction. All right. So at this point, you're probably wondering, what the heck does this have to do with the ocean floor? All right. Well, what happens is when you have lava and the lava is cooling and hardening, some of the minerals harden before the other minerals. So some of the minerals are solid and they're kind of floating around in a liquid of the other minerals. That gives them the abilities to move. And if those minerals that are floating around are magnetic, what will happen is they'll end up pointing towards the north magnetic pole, just like a compass needle. And then when that rock completely hardens, all those minerals are going to be pointing in the same direction. They're going to be pointing towards the magnetic north. All right. So right now, any lava, the minerals in lava that's cooling now are going to be pointing to the north. Now, what we also know is that as time goes by, the Earth's magnetic pole every once in a while flip-flops or reverses. Basically what that means, like if you could travel back in time a couple million years and I held a compass out, what I would find is my compass wouldn't point north, my compass would point south. All right, so every once in a while the Earth's magnetic poles flip-flop, the magnetic field reverses itself. All right. Now there's no set time interval for when it reverses itself. So, one reversal might take place 1 million years ago, then the next time it reverses might be 2 million years, 2 million years before that one. The next one before that might be 100,000 years. There's not really a set time interval between when the flips are. Why it flips, scientists don't know about that either. They just know it does flip. Well, anyways, what that has to do with the ocean floor is right now, near the ridge, because that's where the youngest rock is, all the minerals, magnetic minerals, are pointing to the north. But if I go a little bit farther out, over here and over here, I find the magnetic minerals are pointing towards the south. And over here, they're pointing to the north again. And over here, they're pointing to the south again, to the north again, and so forth. So what that suggests then, so the pattern of magnetic orientation on one side of the ridge is like a mirror image of the magnetic pattern on the other side of the ridge. So what that's suggesting then is like both these guys formed at the same time right there, but then got pushed off to the side. Both these guys formed at the same time, but then got pushed off to the side. Both these guys formed at the same time and then got pushed off to the side. Both these guys formed right there, but then got pushed off to the side. So again, because the one pattern of magnetic orientation on one side is a mirror image of the pattern on the other side, that suggests that new rock's coming up like that and then spreading like that. Right? So that's another piece of evidence that the ocean floor is spreading apart. Right? All right, next. Another major change, continental drift. Major landmass is soon to be moving around. All right? Now, for the longest time, people thought that it's impossible for continents to move because they're big, giant, massive things, and what could move them? How could they possibly move? But there's actually a few simple observations you can make, excuse me, that would lead us to believe that the continents are in fact moving. And it has to do with the shape of the continent and looking at the fossils and the rocks on the various continents. So let's go back to looking at a map of the world. All right. All right, so we look at a map of the world here. Something that you notice is that if you look at the shape of some of the continents, they really look like they kind of match up with other continents like puzzle pieces. And the most obvious example is like the coast of South America right there and the coast of Africa right there. That's almost a perfect fit and shape to that right there, all right? And there's other places in the world that are kind of like that, but this is the most obvious part. The shapes just seem to kind of match up. And then like if you look at the shape here, that's pretty much the other side of that kind of shape right there. They seem like the opposite side of puzzle pieces. Now, people have had maps been fairly decent for like 150 years or so. So as people noticed this, but they just thought it was a coincidence because again, it doesn't make any sense, if they thought at the time, for these big continents to be moving around. But the more and more you look at the shapes of the continents, the more and more it's like, well, these are an awful lot of coincidences that are happening. Right? Now you tie that in with some other evidence, like for example with fossils. All right, I may dig up and I might find a certain type of fossil over here in Africa, and then I might find the exact same fossil over here in South America. All right. Now, if it was like a bird fossil, you think, oh, the bird could fly across the ocean. But if it's like a land creature over here and over here, the odds of a land creature, swimming across the ocean for several thousand miles is pretty slim. Or this could be like a freshwater clam and a freshwater clam, and then there's a saltwater ocean in between. So there's no way for the clam to get from one side to the other. So it didn't make sense for there to be, the same type of fossil here and the same type of fossil here, unless at one point those two continents were connected and those two continents were moving. Or another thing is if you look at like mountains and so forth, like I could find like a mountain range like here that corresponds to a mountain range over there. It's like the exact same type of rocks on both sides and the exact same rock formations. The odds of the exact same thing happening there and there at the same time are pretty rare. It makes a lot more sense that those things were connected. Or another thing is that you find fossils that don't really match too well their current location. So for example, like in Antarctica, you could find coal, all right? Well, coal's a type of sedimentary rock that forms in warm, swampy areas. Antarctica is not warm and swampy. So that would suggest that Antarctica must have been closer to the equator at one point, right? So things like that, where you're looking at the rocks, how the rocks match up on different continents and the fossils match up on different continents, and just the shape of the continents, how they look like they fit together like puzzle pieces, all those are pretty strong pieces of evidence that the continents were once all connected at one point. And scientists have called that time when the continents were all connected, they call that landmass Pangea. So Pangea is like a supercontinent that had all the present-day continents connected together. Right. Now, why exactly is the ocean floor spreading and why exactly are the continents moving is something that we're going to look at on another day. All right, so for right now, that is examples of major crustal changes, some changes that we can observe, but it takes a bunch of observations from a bunch of different areas to lead us to these ideas here. All right.